Hi everyone. So today let's discuss the Boruvka's greedy algorithm. Yeah, also known as Boruvka's algorithm for the minimum spanning tree. Right. So this is one of the famous algorithm which uses the greedy approach. So we have come across the minimum spanning tree algorithms already. Actually, we have discussed that one in the graph, right? Kruskal's algorithm as well as the Prim's algorithm, if you remember. Yeah, those are one of the this one famous algorithms as well. So Boruvka's algorithm is one of the oldest algorithms. If I want to put it in this way, it's one of the old algorithms. Yeah, it's one of the oldest, you can say. Yep, so this is fine. Yeah, let's move on with the definition part. Let's see what the definition part says here, right? So Borukha's algorithm is a greedy algorithm used to find the minimum spanning tree. Yeah, it's used to find, or it's used to determine the minimum spanning tree of the weighted connected undirected graph, of the weighted connected undirected graph. This one we have to keep in mind. It repeatedly connects each component to the cheapest edge until all the vertices form one connected component. Yeah, until all the vertices form one connected component. Now let's move on with the explanation part, man. Just listen to this carefully. Let's just try to understand or analyze so that this exact same thing will be articulating in the form of code, man. Yeah. So the graph starts with each vertex as a separate component. Each vertex will be split into the separate component here. The graph starts with each vertex as a separate component. In each iteration, for every component, we have to find the minimum weight edge connecting it to the another component. For each component, we'll find the minimum weight edge connecting it to the another component. All will add all these edges to the MST. Will add all these edges to the MST or minimum spanning tree, since they are the cheapest possible for each component. Yeah, for each component, first what we'll do, we'll find the minimum weight edge connecting to the another component, all other components. Yeah, for every component. So we'll do this. Then we'll add all these edges to the MST or the minimum spanning tree, since they are the cheapest possible for each component. Yeah, this is fine, I believe, as we are considering the minimum weight edge, right? So this is fine for each edge. So now what we'll do after doing that, we'll merge the connected components. We'll repeat until only one component remains. That's our MST, right? That's our MST, minimum spanning tree. So this algorithm is efficient for parallel processing and it works in big of E log V time. It works in big of E log V time. So this is fine, I believe. Yep. So now let's do one thing. Let's quickly discuss the this one. Let's quickly write the algorithm. Yeah. The same thing, whatever we discussed in the explanation part, let's try to articulate in the form of code. Yeah. Let's start writing the algo. Yep. By making use of the Python programming language. Just give me a second here. 1 second. Hmm. Yeah, let's start writing the algorithm. So first, let's define the structure of an edge man. Yeah, so I'll just go with here class edge. So this is fine. Now let me go with uh this one in it. So this is fine. Yep. Let me delete this one along with the self. Let me go with the source as well. We need source, destination as well as the weight. So we need source, destination as well as the weight. So this is fine. Now let's go with the initialization part. Let's just go with the source. So this is fine. Also, let me go with the destination. So this is also fine. And the final one is let me go with the weight here. So this one, wait, yeah. So this is fine, man. Now let's do one thing. Let's define the graph. Let's define the graph. So I'll just go with here class graph. So this is fine. Again, the initialization part. So I'll just go with initialization or the constructor part. So this one along with the self, I need vertices. Yeah, we need vertices, right? Obviously. Also, we need the edges. Yep, so this is fine. So within the this one construction part, let's this one constructor part, let's initialize one. So let's initialize the vertex to the this vertices, v to the vertices actually, sorry, and also just to the. So this is fine, I believe. Yeah, we are just going with a list of edges, edge objects. Fine. Now let's do one thing. Yeah, let's write the function to find the parent of the vertex. Nothing but this is for the union find one. We'll be going with a union find. What we'll be doing with the find? Within the find actually, this one. What do we, will be finding the parent, right? So we have to find the representative. If you remember the algorithm, union find algorithm, we have to this one find the parent or the representative. Also, we'll be going with the path compression within the find method. Yeah. So let's do that. Let's write the function. So I'll just go with a find uh, parent here. So this is fine. Let me go with self as well as the parent. Along with the parent, let me go with a vertex. So we have solved n number of problems with a union find that by making use of the union find already. So we have to know the algorithm at any cost, union find algo, right? So let me go with a parent of, let me go with a vertex here. This is fine. If it is not equal to the vertex, if it is not equal to the vertex, then what we have to do, let me go with the parent of, let me pass the vertex here. Let me assign this one to the, actually, uh, find parent here of this one. What we need to pass here, parent along with the, this one parent of vertex. So this one has to be parent of vertex. Yeah. So this is fine. So now all we have to this one after finding the parent, so we have to return this one parent of vertex, right? Particular vertex. Usually, basically, we find what do we do in the find method in the union find? We'll find the representative or the parent or the root actually. Yeah, along with the path compression. Yep. So this is fine. Now, basically, let's write the union as well. So within the union method, what we do usually we'll be going with the union based on the size or the this one based on the rank you can call. Yeah. So now, let's go with the union of two subsets here. So I'll just go with def union. So let me go with self here, this one parent. So this one, as I've said, will be going with the rank along with the variables x and y. Usually we consider x, y. So this is fine. Yep. Now I'll just go with x root. So this one we know. I'll just go with self dot fine. For this you have to know the algorithm actually. So I'll just go with find parent. So this is fine. Let me pass the parent as well as the x. This is fine. Now let me go with y root. So this one will be self dot find. So this is fine. Let me go with a find parent. So this is fine. Let me pass parent along with the parent. Let me pass y. So this is also fine. X root and y root. Let's go with a if condition man. If rank if rank of x root. So this one x root. Um So this one we have to write this one within the square brackets, right? So sorry. Yep. So x root. So if it is less than, so union based on the rank we are going. So this one a rank of y root. So y root we have considered, right? X root and y root are the variables we have considered. Actually, keywords that we have considered are the variables. Yep. This is fine. So now let's go with the parent of x root. Parent of x root. Let me assign this one to the y root. Yeah. So if you don't know this one union, what do we call disjoint set union or the union find algo, so I can just go through the this one graph based playlist, and in that I have explained disjoint set union or the this one union find this one algorithm with the path compression. We have discussed there. You can just go there. This one you can just go to the graph based algorithms and you have you can check there. Yeah. So everything is interlinked. Everything is interlinked. So you can just go and you can just watch the video, man. Yeah, that's what. So you can just come after watching the video, right? So you'll understand this one better. So this is fine. Now let me go with the else if or elif in case of we are making use of the Python, right? So I'll just go with rank of x root here. So this one, if it is greater than rank of this one y root, actually I'll just go with a y root. So this is fine. So now let me go with parent of y root. So this one is fine. Parent of y root. So this one will be x root. X root. Yeah. So next let's do one thing. I'll just go with the else. else. Let me go with the else. I'll just go with the parent of y root, parent of y root. So let me assign this one to the x root. Yep. So finally, let me go with rank here, rank of x root. So this one x root. Let me go with this one, rank of x root equals rank of x root plus 1. So this is fine, man. Now, yeah, we are done with a union method, a union function, or a union of two subsets, right? So now let's move on with the next, this one function. This is going to be the main function, yeah? Main function implementing the Boruvka's algorithm. Yeah, let's write this one. This is going to be fun. Let's write this one. So this one, let me call this one Boruvka, this one, MST, minimum spanning tree. So this is fine. So let me pass cell. So within this function, first thing, let me go with a parent. Um, Let me initialize the parent to the empty array. Also rank to the empty array as well. Then let me go with the cheapest here. Cheapest, let me assign this one to the -1 into we have considered self dot vertices v, big V, right? So we are just storing the cheapest edge for the each component here, right? Next, let's go with the number of trees. I'll just name this num trees. Here, let me assign this one to the self dot v again. Yeah. So this is initially each vertex is a tree, right? So that's what we are assigning this one to the self dot v. This is fine. Now, total weight of MST we have to initialize to something, right? So I'll just consider here MST weight. So let me assign this one to 0, or let me initialize this one to the 0. Yep. Next part is we have to initialize the parent and rank. We have to initialize the parent and rank. So let me go with for node in range. For node in range, I'll just go with a self dot v here. So this is fine. Uh, Next thing is let me go with a parent dot. Let me go with append. This node. This is fine. But yeah, let's move on with this one. Let's append the 0 to the rank. So I'll just go with append of 0. Yep. Now we are done with this part. So let's do one thing, man. Let's print something for the interactive purpose here. So let's display initial number of trees, nothing but the components, right? So let's pass the num trees, whatever num trees itself we have considered this one, right? So let me do one thing. I'll just go with the print here. So let me write the same thing actually. Initial this one number of trees actually, nothing but the components, nothing but the components here. So this is fine. I'll just go with num tree. So this is fine, I believe. Yep. Now let's move on with the next step. Next, let's move on with the next step. We have to continue until only one component remains. Yeah, accordingly with the explanation, whatever we have discussed. So I'll just write the while loop here. While num trees actually, if it is greater than 1, then let me consider for I in the range. In what range we have to go? This one, vertices, right? So I'll just go with self dot v. So this is fine. This v has to be capital. Yep, this is fine. Next, let me go with cheapest of I. Let me assign this one to the -1. Yeah. Now let's move on with the next step here. Now let's move on with the next step. So let me start from here, or else indentation error. So let's traverse all the edges to find the cheapest edge for each component. Yeah, so this one I have to type one. Yeah, let's do one thing. Yeah, but let me type this one. For I in range, so this one has to be length of, I'll just go with the edges here. As we are making use of the class, let me make use of, let me write self dot edges. This is fine. Next, node u, node v, along with the weight w. So let me assign this one to the edges of I dot source, u to the source, this one, what do we call, v to the destination, yeah, this one, v to the destination, and this one w to the weight actually. So this one, the same thing, man. Let me copy this one actually, src. So here, let me paste it over here. Instead of source, I'll change this one to the destination. So this remains same. Again, let me paste this one. Instead of source, I'll change this one to the wait actually. So all other things remain same. This is fine. Self-product just of I. Yeah, self-product just of I dot destination. Source destination as well as the wait. Yep, this is fine, man. Now let me go with the set one. Let me assign this one to the self dot find. Mm, Let me go with the find parent. Yeah, we already have this one. Let me pass parent as well as the this one node u. The same thing. Let me paste here. Let me change this one to the set two find parent instead of the this one node u. I'll just change this one to the v. Yep. So this is fine as well. Now let's write the simple if condition. If set one, if it is not equal to set two, this is fine. Then let's write the simple if condition. This one if cheapest of the set one actually, cheapest of the set one, if it is equivalent to the value minus one, or let me go with edges here, edges of the cheapest of the set one, cheapest of the set one. So this is fine. Dot weight. So I'll just go with a weight. I'll just go with a weight. If it is greater than W, then what we'll do here? Let me go with the cheapest of set one. Uh, Let me assign this one to the I. So this is fine. Yeah, let me go with one more if condition here. If uh, cheapest of the set 2, let me go with the set 2 here. So equal to minus 1 or self dot. So this one, I'll just go with the edges. So this one will be cheapest of this one, set 2, set 2. This is fine. Dot weight. So I'll just go with the weight here. Weight, what if it is greater than W? What if it is greater than W? I should have copy pasted the same thing and made the necessary changes. Fine. So let me copy the same thing here and let me write it over here. Instead of this one set one, I'll just change this one to the set two. This is fine. Yeah. Now let's move on with the next step. Let's move on with the next step. Yeah. So just give me a second here. Yep. Let's move on with the next step. So we have to add the cheapest edges to the MSD man. So we are almost at the last this thing. All we have to do is we have to add the cheapest edges to the MSD. So I'll just go with for node in range vertices we have to consider dot v. So this is fine. If let me go with the cheapest, if cheapest of node, if it is not equal to minus one, then what I need to do here, let me assign u to self dot edges. So this is fine. Let me call here cheapest. Also, let me go with the node. Yeah, this is fine, man. Cheapest of node we have to go with, right? So this one I have to close here itself. Here, sorry. So I'll just give here dot src. So this one has to be set one, not the cell actually. This one has to be set one. This is fine. This one has to be self, right? Sorry, thinking something else. So this is fine. Let me copy the same thing here twice. So let me change this one to V, node V and the weight W, right? So this one will remain the same. Cheapest of node, not this one. Instead of the source, let me change this one to the destination. Also, instead of the source, let me change this one to the weight actually. Yeah, this is fine, man. Now let's do one thing. Let me assign set one to self dot find. So this one find parent. So this is fine. Let me go with the parent comma u. Yep. So let me copy the same thing and make the necessary changes. So this one has to be v, and here we have to change this one to the set two. Yep. Find parent parent v. So this is fine, man. Now let me write the simple if condition here. What if set one is not equivalent to the set two? one, if it is not equivalent to the set 2 actually, then what we will do, let me go with self, let me go with self dot uh, union. So union, so this one will be parent. So we have to pass a rank as well. So we have already written union helper method here somewhere. This one we are considering rank along with a self parent rank xy, right, parameters. So this one, let me go with a parent rank instead of the xy. Let me go with the set one as well as the set two. Yep. Now what we need to do? Sorry. Why did I remove this one? So let me go with a print actually. Let's print something for the interactiveness here. So I'll just start with F as we'll be making use of the string interpolation here. So I'll just go with edge. So this is fine. Let me go with the U. This is also fine. Let me go with V here. Let me go with a V here. This is also fine. Yep. So this one will be, let me give with weight W, with weight W, added to the MST. Something I did something wrong. I don't know what thing I did wrong. So let me change this one to here actually. Let me give here. So this is fine. And also let me close the parenthesis over here. So this is fine now. Yep. That's the reason we were getting error. So I'll just go with a MST, minimum spanning tree weight, equals minimum spanning tree plus this one W. Yeah. So this is fine. The final one is, let me consider number of trees, num trees here. Num trees equals num trees minus 1. Yeah. So finally, let's do one thing. Let's print something for the interactive purpose. Yeah. So let's do one thing. So I'll just consider here. Yeah. Let's do one thing. Let's print something for the interactiveness one. So this one, let's print in the new line. I'll just make use of the slash in here. So this one will be final MSP. I'll just go with a weight. This is fine. Let me pass MST weight here. So this is also, yeah. Now we are done with the algorithm one. So this is it for the algo. I have explained this one step by step. And we have made use of this one, a disjoint set union here, or the union find, right? So yeah, this is the main, this one, what do we call? Main Boruvka set, this one, Boruvka MST function actually, to calculate the MST. Yep. So basically this completely uses the disjoint set union along with the greedy, right? So this is completely based on the greedy approach. Yeah, along with the disjoint set union data structure. So this is fine. Now, let me take the example usage from the Google. Just give me a second here. So let me paste it over here. So this is the example graph actually. Yep. So this is the simple example that I've considered here. Right. So this is fine, I believe. So now we have the idea on the algorithm, complete idea on the algorithm, basically which uses the disjoint set union, and it is completely based on the greedy approach. Yeah. So what is the output that we need to get? So let me draw this one actually, whatever the this one we have considered here. So first, this is undirected graph, right? So this is for the undirected graph, 0 to 1 actually. This is fine. 0 to 2, we have, this is also fine. 0 to 1, we have the value 10 or the weight 10. 0 to 2, we have the value 6 or the weight 6. 0 to 3, let's consider. So here, let's go with the 0 to 3 with the value, this one, value 5 actually, this is fine. And 1 to 3, we have this one. I can just consider in this way. 1 to 3, we have the value 15. Yeah, we have the value 15. And 2 to 3, I can consider in this way. 2 to 3, we have the value 4. Yeah. So this is the graph. So this is the graph. It is undirected. Yeah. So this is the graph, undirected graph. Yeah, we have 10, 6, 5, 4, and 15 values. 10, 6, 5, 15, and 4 actually. It is nothing but for the 2 to 3, right? Yep. So this is fine. For the 1 to 3 or 3 to 1, we have consider this one 15. Yeah, this is fine, man. So this is the graph actually. So what is the output that we need to get? Basically, we are calculating the MST weight, right? Minimum spanning tree weight. So first what we are doing, we are printing the, if you remember, we are printing initial number of trees. We are printing initial number of trees, nothing but the components, right? Components here, we have four components. Uh, we have four components here. So when I say we have four components, meaning, so each vertex or each node is its, this one. Each vertex or each node is its own tree, right? So we have four, this one vertex here, 0, 1, 2, and 3. So initially, I'll just write int, nothing but the initially here. Yeah, intl, let me write. Initially, we have four components. Initially, we have four components. Each vertex is its own tree. So we have to get here initial number of trees components is nothing but the four, right? Print statement, we are this one. We are going with the print statement for the interactive purpose, right? So in that, I have written in the strings initial number of trees components, nothing but in this case we have to get four, because this one, each vertex is its own tree. We know this one. Next, we are considering the this one. What do we call? Um, we have to go with a final MST, this one weight, right? First, we will consider edge, this one 2 comma 3. First, we will consider edge 2 comma 3 with a weight 4, with a weight 4, that is added to the MST. First, we will consider edge 2 comma 3 with a weight 4, right? Then we will be considering edge 0 comma 3, edge 0 comma 3, right? So edge 2 comma 3 is having the this one smallest actually. Yeah, here you can see value weight 10, 6, 4, and 15, and 2 comma 3 is having the smallest weight 4. First we'll consider edge 2 comma 3 with a weight 4. Next we will consider this one, 0 to 3 actually. 0 to 3 is having the weight 5. Among the this one weights, the smallest weight is 4. The second smallest one is 5 here, from 0 to 3, as it is undirected. From 0 to 3 with a value 5 actually, with a weight 5. Edge 0 comma 3 with a weight 5 added to the MST, and uh, we will be going with the next smallest is 6, from 0 to 2 or 2 to 0, anyhow, this one. Or we have to consider 10 here, right? So this, this one, yeah, we have to consider 10 actually, from 0 to 1. Edge we will be considering actually from 0 to 1. Yeah, 0 to 1. So this is interconnect basically. We are going with the minimum split, right? So we'll be going with the edge 0 comma 1 with a weight 10, with a weight 10 that is added to the MST. So overall, so final MST weight would be, so it would be, so this one, we are going with a 4, as well as the edges, right? Four, initially four components we have to get. Then edge 2 comma 3 with weight 4, this one we are printing, right? So this is fine. Edge u, the edge weight added to the MST, this print statement I'm speaking of, this print statement. Yeah. So this one edge, this one 2 comma 3 with weight 4 added to the MST, edge 0 comma 3 with weight 5 added to the MST, edge 0 comma 1 with weight 10 added to the MST. So final, why we are considering 2 comma 3, 0 comma 3, and finally 0 comma 1, not the 0 comma 2. See here, the cheapest edges connecting different components will be chosen here. 2 comma 3 we have weight 4, 0 comma 3 we have this one, what do we call, weight 5, and 0 to 1 also we have to consider. From 0 to 1, the weight, the cheapest weight we have here is 6 actually. Sorry, we have 10. Not, we are not going with the smallest. Smallest from 2 to 3 we are considering. 2 to 3 we have the smallest 4, and 0 to 3 we have the 5, and from 0 to 1 we have the smallest 10. We have the smallest 10, right? So this is fine, I believe. From 0 to this one we have the weight 10. Yeah. So we are getting the cheapest edges connecting different components are will be chosen actually. So we have chosen here 2 comma 3, 0 comma 3, and 1 comma 3 with the weights 4, 5, and 10 respectively. So as these are added, components merge into one connected structure, right? Uh, Once only one component remains, the total MST weight becomes, so this one we have to add this one. Once only one component remains, so here we have to get the, we have to calculate the total MST weight, nothing but here in this case, when one component remains, it will be 4 plus 5 plus 10, it will lead to 19. It would lead to 19. So totally at the end we are printing this one, final MST weight, this line, final MST weight, nothing but we are passing MST weight, right? So this will be, calculation will be 4 plus 5 plus 10, that would yield to 19. So this is the output that we need to get, right? So what is the output that we need to get here? initial number of trees, nothing but the components is 4. Then h2 comma 3 0 comma 3 0 comma 1 with a weight 4 5 and 10 added to the MST. That sentence we have to get 3 sentence. Along with them, the final one will be the final MST edge. So we got here 4 plus 5 plus 10, nothing but that would yield to 19. Yeah, so this is the output that we need to get. Yeah, so let's do one thing. I'll just come here. Let me copy the entire this one. As we have the complete understanding of the algo, we give control J. Let me give Python followed by the file name.py. Yeah, so here we have some error. Graph object has no attribute V. Did you mean V? Yeah, we have capital V. Where I have done this one, 56 actually. 56. Oh yeah, self dot. Let me go with the capital V here. So this is fine. Now let me give clear screen and let me run this one again. Yeah, now we are getting the correct output. See here, initial number of trees components. Each vertex is its own this one, right? What do we call that one? Each vertex is its own tree initially. So 0, 1, 2, 3. So we have 4 vertex. So we have to get the this one 4. At 0, comma 3, this one, why we are getting in this way? Edge 0, comma 3, 1 second. So this one, let me remove this one. Let me give clear screen here. This is fine. Let me run this one again. Yeah. Now add 0, comma 3 with the weight 5 added to the MST. This one first we are getting the order doesn't matter here. 0, comma 3, 0, comma 1. First I said this one actually 2, comma 3. Then I said 0, comma 3 and 0, comma 1, right? So first we have considered this one. Second we had considered this one. And finally we had considered this one. The order doesn't matter here. At 0, comma 3 with the weight 5 will be added to the MST. This one 0, comma 1 with the weight 10 will be added to the MST. Final edge 2, comma 3 with the weight this one 4 will be added to the MST. Final MST minimum spanning tree weight has to be 19. 5 plus 10 plus 4, or we went with 4 plus 5 plus 10. That is fine. Anyways, order doesn't matter here. Final output, final MST weight that we need to get here is 19 and 19. So we are getting the desired output. So these two things, component 4, 19, and that just we are getting the desired output. This is this works, whatever the algorithm that we have written works flawlessly, right? So yeah, we are done with the algorithm. So this is it, man. This is it actually. So as we have complete understanding of the algorithm and we have seen the output, let's do one thing. We are done with the algorithm part. So let me summarize whatever we have learned so far before moving on with the other algorithm. Next algorithm, let me summarize whatever we have learned so far, right? So there are some points we have to remember or we have to know at any cost. Actually, there are some 4 to 5 points that I want to discuss with you guys. I wanted to discuss with you guys. So let's discuss the same actually. First point here would be, so Boruvka's this one, what do we call? Yeah, Boruvka's algorithm builds the MST by repeatedly adding the cheapest edge from the each component. Yeah, cheapest edge from the each component. Yeah, from each component. So this is fine. This is one of the important things. And second point is it merges components until only one remains, until only one component remains. Yeah, so this is fine, I believe, until only one component remains. The third one here, the time complexity of this particular algorithm would lead to biko of E log V, biko of E log V, and the space complexity would lead to biko of V plus E, biko of V plus E, right? So the space complexity would lead to biko of V plus E, and the time complexity would lead to biko of E log V, right? So this is going to be the time complexity, and this is the space complexity of the algorithm that we have written. So the final step would be, or the final point would be, so let's discuss the use cases. So this is useful in parallel and distributed systems. Yeah. So this is useful in parallel and distributed systems. Yeah. Due to its independent component based approach. So this is useful in parallel and distributed systems due to its independent and component based approach. So this one, this is fine. Yep. Yeah, so these are some of the important points that I wanted to discuss. You have to know these things. Yeah, so this is fine, I believe. So we are done with the Boruvka's greedy algorithm, and also this is going to be the last algorithm within the greedy based algorithms playlist. Yeah, so we are left with only this one. What do we call? Three most important this one. How do we say that? Playlists actually. we are left with number theory algorithms, geometry algorithms, and advanced or miscellaneous algorithms. Yep. So we are done with almost all the important algorithms, man. We are left with only the last three. So we started with array algorithms, then we went with the string algorithms. So sorting algorithms, searching algorithms for the fourth playlist, fifth playlist for linked list algorithms. Then we completed stack and queue algorithms. Then we this one discussed the tree-based algorithms. Then we went with a previously we went with a graph-based algorithms. Yeah, so that was one of the huge this one. We had around 20 algorithms. Important this one 19 or 20 algorithms, right? So now recently we completed dynamic programming algorithms, DP algorithms. Then today we are completely we are finishing this one greedy algorithms playlist with this particular algorithm minimum spanning tree Baruka's minimum this one greedy algorithm on the minimum spanning tree, right? So this is completely fine. We are completely done with the greedy based algorithms. Yeah, with the Baruka's this one algorithm. Yep. So next we will be discussing on the topic this one number theory algorithms. So in number theory algorithms, we almost have 12 to 13 algorithms. Let me name this one just for the this one just for the sake, right? Uh, so first we'll be going with a sieve of Eratosthenes. Next we'll be going with this one segmented sieve. Then we'll be going with this one Euclidean algorithm to find the GCD basically greatest common divisor. Next we'll be going with the extended Euclidean algorithm, which is very important for the CP. So for the CP actually sieve of Eratosthenes segmented sieve, Euclidean algorithm, extended Euclidean algorithm. Modular exponentiation is very important when it comes to this one optimization. Modular exponentiation, you have to know it at any cost. Modular inverse as well as the modular exponentiation. Then we'll be discussing on the this one Chinese remainder theorem. Then we'll be going with a Euler's totient function. Then we'll be discussing Miller-Rabin primality test. Yeah. Then we'll be going with a Pollard RHO factorization. Then we'll be going with a fast Fourier transform. Finally, we'll end the playlist with this one number theoretic transform. Yeah, these are some of the algorithms we'll be discussing in the number theory algorithms playlist. Yeah, so today let's finish it off this one greedy based algorithms with this particular algorithm, this one Baruka's algorithm. Yeah, for now, this is it. Thanks for watching, guys.